Hi all, this is Mr. Yeager for AP Physics, continuing our unit on fluids and talking primarily about buoyancy today, okay? Getting these objects to float or being submerged under water and going, why are they floating even underwater and so forth. So we are introducing this force, the buoyant force, okay? It's created by an object when it is submerged. It doesn't have to necessarily be completely submerged, it just has to at least be partially submerged, okay? To obviously feel the buoyant force, all right? The reason that the buoyant force is created is based on what we said with our last video. The pressure at the top will be less than the pressure at the bottom. Okay? As we said, as we go down farther, the pressure increases. And therefore, there's a greater pressure on the bottom, which is going to push the can upwards. And this is creating what we call the buoyant force. Okay? Excuse me. So we label that FB. The formula for buoyant force is rho VG, okay? So volume of the fluid and the density of the fluid is what we're looking at with it. The mass or shape of the object that is on the fluid clearly is not in this formula, okay? So we're not worried about that if you're given the mass of the object in the end. It's going to be related to how much of the volume is displaced on it. And so that's where we introduce Archimedes' principle. The buoyant force on an object immersed in a fluid is equal to the weight of the fluid displaced by that object. Okay? And so you might be going, wait, well, wouldn't that be related to the mass of the object then? It says weight of the fluid. Okay, the weight of the fluid displaced. So let me kind of illustrate why that is. Okay? So we have buoyant force equals rho VG. We did something similar, I kind of did the opposite, showed starting from force, gravitational force to this. I'm going to go backwards now. We know rho is equal to m over v. So if I plug that in, I'm going to get m over v times vg. Well, what happens to the volumes? They cancel out, and I'm left with m times g. So the buoyant force is again equal to, this is the mass of the liquid times g, okay, that's acting on the object. All right, again, this is the liquid acting on the object. That's the force pairing. All right, so if I give you this question, pretty quick here. A metal cube with a volume of 0.02 meters cubed is submerged in the liquid. If the buoyant force acting on the cube is 150 newtons, what is the density of the liquid? Okay, so I have my formula, rho Vg. I know the buoyant force, 150. I know g is 10. The volume is going to be 0.02 because that is the volume that would be displaced. If I put that object in, it must take up that amount of space and push that equal amount of volume away, okay, of fluid. And so I can solve, and this comes out to a density of 750 kilograms meters cubed, okay, per meter cubed. So this is not water, okay? Water we said was 1,000. So this must be some other oil or less dense fluid, like maybe an alcohol or something that is in place, that this object is submerged. All right, getting into floating, okay, and why do objects float? Well, again, in chemistry we kind of just go with the idea that if it has a larger density, it should sink, okay? And so if I have an increased density, more of it should be able to submerge in the liquid. Obviously, if it's greater than the density of the liquid or the fluid, it should completely sink to the bottom, okay? So what we're going to be calculating quite often is how much, what percentage of the object is submerged. And we can use this relationship, okay? This is basically the buoyant force of the fluid, and this would be the countering of it. Okay, basically how much force is acting back against it. That would basically be the weight of the object, okay, is what you're looking at there. All right, and so we can relate the two. Again, subscript F is fluid, subscript O is the object that's floating. So we can cancel the like terms, and then we like to move the same terms to the same sides. And so you can see the setup here, where we get this ratio. This is a very important derived ratio, that the volume of the fluid over the volume of the object is equal to the density of the object over the density of the fluid. Okay? So they are, the object and fluid are reciprocals on either side from volume and density, okay? It's not fluid on top on both. So you can try to just remember, hey, if I put fluid on top here for volume, I need to put fluid on the bottom on the other side. But this part right here with the volumes, this VF over V naught times 100, that's going to equal the percent of water displaced. Okay? That's going to equal how much water, what percentage of water has moved away from the object, and therefore how much is submerged of the object. Well, you'd have to go back and maybe go, okay, if that's how much water got displaced, again, that's how much, sorry, that is how much should be submerged of the object. Okay? So that's a nice formula. So we got a quick problem here. A plastic ball with a density of 800 kilograms per meters cubed is floating in oil with a density of 900 kilograms per meters cubed. What percentage of the ball is submerged in the oil? Well, we're given the densities, so we don't really have the volumes, but I can do the density side, okay? And all I do is 800 divided by 900. I don't have a time, this should be times 100. Okay, don't be too confused there. And that'll give you 88.9% of this should be submerged, okay? It should still have some of it above water, which we would say is floating. I mean, the whole thing is floating, okay? But base almost 89% of it is underneath the water at that time. It's like an iceberg, okay, is what we're looking at there. So it's very close, but not equal, and should be floating on top, okay? Two more problems, okay? I'm going to work these two out, so I'll have to go back to a separate page. So, a boat with an area of 1 meter squared and a length of 3 meters is floating on the water. The boat has a density of 500 kilograms per meter cubed. How many people, each with a mass of 100 kilograms, could be on the boat, could the boat support before it would sink? Okay? So, we're trying to figure out, basically, how many people can I get on this boat before it sinks? In other words, I want the people to essentially equal the buoyant force, or how much force can actually be, you know, sorry, I'm not saying this very well. We are essentially trying to figure out where the buoyant force is equal to the weight, is really what we're trying to figure out here. Okay, so if I basically broke this down, whoop, that's another problem we're going to do on a different video. All right, so I have my boat. It looks amazing, okay? And so with this boat, what we got, okay, is we're trying to figure out how many people are going to go on it. And every time people start going on it, obviously there's going to be greater volume displaced, all right? The boat's going to be pushing down farther into the water, all right? And we want to basically figure out when, at a certain point, the buoyant force is equal to the weight, the gravitational force. That's essentially what we are doing here, okay? The full amount of it, all right? So what we can do, okay, is we also need to figure out the volume that is displaced, which would equal then the volume of the boat. Because once I have the whole boat underwater, that's the total volume that's displaced underwater. So I can do that by simply doing, so I'm going to go back. I have the area of the boat and then the length, that would be height, whatever you want to call it. So the volume of the boat is simply 1 times 3. So 3 meters cubed, okay, is the volume of the boat. All right? So if I'm doing buoyant force equals gravitational force, I'm going to be doing rho Vg equals mass times gravity. Okay? And so I'm going to cancel those out. Okay, G can cancel. I know the density of water is 1,000 times 3. Okay, that would be the total amount of water to completely, that the boat would be underwater and displacing all that water. And so this mass of fluid is equal to, because that's technically what I'm solving for here, the mass of fluid is going to be 3,000 kilograms. Okay, so I need to displace 3,000 kilograms of fluid. So I need 3,000 kilograms of object, okay? And so to figure that out, I need to go back. I'm going to kind of erase this real quick so we're not getting too confused. I need to figure out the mass of the boat. The density of the boat is 500. So density equals mass over volume. So 500 equals mass over 3. That's the volume of the boat. So the mass of the boat is 1,500 kilograms. So if I subtract that from the total amount of water that needs to be displaced, I need another 1,500 kilograms. Well, if each person is 100 kilograms, 1,500 divided by 100, I need 15 people. So if there's 1,500 kilogram people on this boat, the boat will officially be sunken in the water with the people. All right, hopefully that does not happen. Okay. What about the second one? A mass of density, I should say, has a density of 1/4 that of water. And it's tied to the bottom of the container as shown in the following diagram. What is the tension in the cord that is attached to the mass? Okay, so this one, I don't think I need to go to another page. All right, so for this one, the object has less density than that of water. So if it wasn't tied to the bottom, it should be floating, okay? But it's tied. So what would be the forces acting on it? It would be the gravitational force of the object itself. The tension would be pushing down as well, or pulling down, and then you have a buoyant force up, okay? And since it's not moving, these forces should equal each other. The buoyant force should equal the gravitational force plus the tension. All right, and again, I'm looking for the tension. All right, so what I can basically do here is, and again, some of this you could probably be more intuitive pretty quickly with it, is I'm going to go mass of the object, okay, divided by volume is equal to, because that's the density of the object, it's 1/4 that of the mass of the water over the volume of water, okay? And so what can happen here is, when it's underwater, those volumes are equal to each other. So we're basically saying the object has 1/4 the mass of the water, okay? It has 1/4 mass. So therefore, it has 1/4 of the weight of the water. And so therefore, again, because buoyant force is equal to the weight of the water that is displaced, if this is only 1/4 the weight of the water, I need basically tension to be 3 times that amount to hold it down. So obviously giving the total amount. So it's the other 3/4 of the weight of the water. It's holding against. All right. So the last thing is there are a lot of good simulations on a website called Physics Aviary. I will just kind of shout them out. You know, they do a lot of quick little simulation things that are nice. One of the things I'll just show here, and you know, is you can start this, and then they have a graph down here that's created, and obviously what you see the force, the tension force is decreasing as the object goes into the water. Okay, and then there's a certain point where it's not going to be holding any more of it. Okay, or holding only partially of it, even in the water. Okay. So the buoyant force does have a maximum amount eventually. It's not necessarily going to hold it all. Like based on this, if it lets go, it should actually sink to the bottom. But you can see that obviously we can figure out the buoyant force by doing that and going, okay, or the mass of the object and go, well, if there's still a 5 Newton tension force, the buoyant force must be 5 Newtons acting on it. So again, and that, you know, if we kept on lowering and lowering it, we should actually see that continue to get a higher and higher and higher. Or sorry, yeah, basically the graph should keep going down. The tension should decrease. All right, so that's pretty much it. Thank you.